Is for students of the second level course on the history of mathematics. It discusses different features of the numeral systems of the ancient Babylonians, Egyptians and Greeks and explains the Hindu-Arabic origins of our own number system.
Suppose we tried to convey to other intelligent beings out in space the fact of our existence on Earth. What signals would we transmit? It's most likely that we transmit some sort of numerical information. Perhaps triples of numbers showing that we can add. This is easy to do by just repeating the same signal to represent different numbers. We might even use a special signal to distinguish tens from ones, and so suggest that our number system is based on 10. But if we were indeed limited just to two symbols and the repetitive principle, then of course we'd find quite simple calculations involving, say, just multiplication, very awkward and time-consuming, unless of course we had some sort of mechanical aid. But the fully developed decimal system has really got much more to it than the primitive system that we might try to communicate to other beings in space. One of its great advantages is that at a comparatively early age we can learn how to carry out the basic operations of arithmetic very simply indeed, just using pencil and paper. To do such calculations, we need to be familiar with multiplication tables, to know the different symbols from 1 to 9 and the symbol for 0, and to be able to add. But the really vital characteristic of our system is place value. A numeral on the right represents units. In the next place to the left, tens, then hundreds, thousands, tens of thousands, and so on. So, with just our 10 different symbols, we can represent any number we like, no matter how big it is, because of the place value principle. So these symbols, 4, 5, 0, 6, mean 4 times 10 cubed, plus 5 times 10 squared, plus 0 times 10 to the 1, that is no tens, plus 6 times 10 to the 0, that is 6 units. But we haven't always had such a convenient and sophisticated system of writing numbers. The idea of counting by tens is very old indeed. It goes back to times long before we have any kind of written evidence. To find out about early systems of writing numbers, we turn to Professor van der Waarden of Zurich University.
Well, the oldest text in which we find written numbers is a Sumerian text from about 3000 BC or even older. It was written in Sumer, which is a country in the south part of Babylonia, where the Euphrates and Tigris come together. You may know the country from the Bible because Abraham came from Ur of the Chaldeans, and that is approximately in that country. Now, when you look at this tablet, you will find in the middle column, from bottom to top, you will find the numbers 1 to 9. That is 1, 2, 3, 4, 5, 6 is missing because it is broken off, and then 7, 8, and 9. The numbers were written just by repetition of one and the same sign, and this sign was written in clay by means of a stylus. When the stylus was put in this slanting position, you got the symbol for 1, and this symbol was repeated any number of times. Another symbol was formed by the same stylus by pushing it in vertically, and this gives you a circular impression, and this means the number 10. This sign too was repeated just as many times as was necessary. At the time when this old tablet was written by the Sumerians, they used two different kinds of stylus. One round stylus for writing numbers, and another wedge-shaped stylus for writing words. The words consisted of wedges. For the sake of convenience, they afterwards, the same Sumerians dropped the round type of stylus, and they wrote numbers also composed from wedges. And this method of writing words and numbers was taken over by the Babylonians in the old Babylonian time, say 1800 BC and even later. One wedge meant 1, and when they wanted to write the number 3, they wrote 3 vertical wedges. And another kind of wedges, which is the L-shaped wedges, they were used for the number 10, and the two symbols were combined to write numbers up to 59 in the decimal system. For instance, 23 was written as 2 L-shaped wedges and 3 vertical wedges. But from 60 on, a new phenomenon happened. The number 60 was considered as a new unit and was written by writing just one wedge. Sometimes you can distinguish between 60 and 1 because the wedge for 60 was written in a larger type. It was a larger wedge. But sometimes you could not distinguish. When you have just one wedge, you never know whether it means 1 or 60 or 60 square. You have to see this from the context, from the order of magnitude of the number. When the Sumerians or Babylonians wanted to write larger numbers, let us say, for instance, the number 81, they divided it into parts. 81 was divided into 60 and 21. And they wrote one wedge for 60, and then 2 L-shaped wedges for 20, and again one wedge for 1. And now you see that the same wedge has 2 different significations. When it stands in one place, it means 60, and when it stands at the end, it means 1. That is, this system of writing numbers is the oldest example we have of a place value system. It's just as in our decimal system. When we write 22, the first 2 has the meaning 20, and the second 2 looks just like it, but it stands on another place and it means 2. And by this method, the Sumerians could write numbers up to an arbitrary height. They had a system with the base 60. You might ask the question, how did they distinguish between 60 square plus 10 and 60 plus 10? 60 square is written as a wedge and 10 is written as an L-shaped wedge. How do you know whether this first wedge means 60 or 60 square? Well, for that purpose they had a kind of zero, a symbol which was placed in between the two symbols, and which means there is nothing in the 60 place. The main differences between the Babylonian number system and our number system are, first, that we use the base 10 and they use the base 60. And secondly, that for numbers below 60, they use a mixed system. First, they jump from 1 to 10, and then they jump from 10 to 60 by a factor 6. But there is one thing the two systems have in common, that is the place value system. The Egyptians had a number system based on quite a different principle. We have Egyptian mathematical texts from the time of 1700 BC, so about the same time as the Babylonian mathematical texts. But the Egyptian mathematical texts were on a much lower level than the Babylonian ones. The Babylonians had an algebra, they could solve quadratic equations. The Egyptians' mathematics was much more primitive, and so was their number system. It was a purely decimal number system like ours, but it was not a place value system. They had separate symbols for 1, 10, 100, 1,000, up to 1 million. The symbol for 1 million is a man throwing up his hands saying, "What a large number is this?" As if, I suppose that this symbol, I'm not quite sure, but I suppose it was not used for actual calculation, but maybe only for boasting. Other numbers were written by repeating these symbols. When they wanted to write the number 30, they repeated the symbol for 10 3 times. And thus, it was not a place value system, it was a decimal system, but it was comparable with the Roman numerals. You may be interested to know whether there was any influence from astronomy to mathematics in Egypt or Babylon. The answer is no in both cases. In Babylon, scientific mathematics started very early, about 1800 BC, whereas scientific astronomy using mathematics starts much later, say 500 BC. And in Egypt, practically no scientific astronomy ever existed. They had mathematics, they were able to solve linear equations with one unknown. It was more primitive than the Babylonian mathematics, but it was certainly not influenced by astronomy. And in Greece, the situation was similar. The Greeks had good mathematics, geometry, and arithmetics already in the time of Thales and the Pythagoreans. But Greek scientific astronomy begins in the time of Plato. The Greeks' system of numerical notation was much better than that of the Egyptians, because they wrote just one Greek letter. They need not repeat a symbol several times. For the numbers from 1 to 9, they had the Greek letters alpha, beta, gamma, etc. And for 10 to 90, they had the Greek letters iota, kappa, lambda, mu, etc. And for 100 to 900, they had 9 other symbols. So they could write, for instance, a number like 41. They wrote it as mu alpha. It was a completely cipherized system, but it has no place value. The letter for 20 was a different letter as the letter for 2. But it was nearly as convenient as our system. This system was the Athenian system of numerals, and it was used in the time before Plato. But 6 centuries later, in the time of Ptolemy in astronomy, a symbol for 0 was introduced. It was just a little circle, and it was used just as in Babylonian numerical notation as a symbol for a missing place. For instance, if you had 1 degree and 0 minutes and 30 seconds, you wrote the sign for 1, and then the sign for 0, and then the sign for 30. It's interesting to discuss the advantages and disadvantages of the several methods of writing numbers. And for this purpose, I shall make one and the same calculation, 12 times 12, according to the Egyptian manner, to the Babylonian way, to the in the Greek way, and in our modern way. I'll show you this on the blackboard. Let's first discuss the Egyptian system. An Egyptian would multiply in this way. He has to multiply 12 by 12. He writes 1 times 12 is 12. Then it is doubled. 2 times 12 is 24. This sign means 10 and these signs mean 1. So this is 20 and this is 4. Then he again doubles. 4 times 12 would be 48, obtained by doubling this number. And then he again doubles it. 8 times 12 is 96. And now he adds this and this. He gets 4 times plus 8 times 12. He gets 12 times 12, and the result of adding up is 144. This calculation is in the Papyrus Rind, written about 1700 BC. Now, how would the Babylonian make the same calculation? 12 times 12, ara means times. He would take a table of multiples of 12, and in this table he would find the result. 2 times 60, that makes 120, and 20 makes 140, and 4. He would find the same result in the sexagesimal notation. Now, how would a Greek make the same calculation? He would write 12, the sign iota means 10, and the sign beta means 2. So 12 times 12. He would first multiply this 12 by beta, that is by 2. Twice 12 will give 24. The sign for 20 is kappa, and the sign for 4 is delta. So we have here kappa delta, and then he would take 10 times 12. So we have to add 24 to 120. And that gives, of course, 100. 20 and 20 is 40, and 4. And that gives 144. Mu is the symbol for 40. Now let's compare this with our method of calculation. You all know this. You write 1, 2 times 1, 2, and you multiply. 2 times 2 is 4, 2 times 1 is 2, and below you write 1, 2, and you add and you get 144. the same result, of course, but the advantage of our modern method is that we need only 9 symbols, whereas in the Greek method you need 27 symbols, or rather we need 10 symbols because we need a symbol for 0. The Greeks didn't need a symbol for 0.
But there's still a number of interesting questions that we can speculate about. Take the Babylonians, for example. Why didn't they have more cipherization? And then the Egyptians. Why was their system of mathematics so rudimentary? And why didn't the Greeks incorporate a place value system? After all, they knew all about Babylonian mathematics. These questions are very interesting, but of course what we're really interested in here is where did our own decimal place value system come from? And to answer that question, we've got to turn to the Indian subcontinent. The symbols themselves can be traced back to beginnings in the Brahmi decimal symbols, though we can see traces of the repetitive principle here in the symbols for 2 and 3. Full cipherization had certainly been accomplished by the 6th or 7th centuries AD, by which time there was also a 0. The decimal place value system diffused westwards. We have examples of numerals in West Arabic manuscripts. The numerals took their place in Arabic culture alongside the Greek alphabetical system, which the Hindu system displaced. The Hindu system diffused to Europe chiefly by way of Italy and Spain, and we have a 10th century example of numerals in the Codex Vigilanus. The numerals took on their familiar form following the invention of printing. Prior to the arrival of the Hindu decimal place value system, Roman numerals were in use in the West. But of course Roman numerals are much more cumbersome for calculation than, for example, the Greek alphabetical system. But the difficulties were minimized by the use of counting boards. Now, the Roman system is decimal, and so the counting boards were divided into columns for units, tens, hundreds, thousands, and so on. Addition and subtraction were very easy, but multiplication, and more especially division, presented a lot of problems. But using a counting board and just writing down the answer, of course, doesn't preserve any written record of the stages of a calculation. And so it's small wonder that the Hindu place value decimal system was strongly advocated by Western mathematicians. Simon Stevin, for example, urged not only the use of decimal numbers for calculations, but he also suggested that even astronomical units should be divided decimally. But despite the obvious advantages of the decimal system, old habits of centuries change only very slowly, and fractions in non-decimal form are still a commonplace today. The sexagesimal system still survives in our division of an hour into minutes and seconds, and in our corresponding division of the degree of an angle. Many commercial weights and measures are still non-decimal, and it's only comparatively recently that British currency has been decimalized. We may live in a largely decimal age, but the Babylonian and even the Roman heritage still survives.
In fact, for any prime order, there's only one group, the cyclic group. Well, of course, there are infinitely many prime numbers, so we know all about the groups for infinitely many orders. Not a bad day's work.